Hello students, hi. This is Jagan Babu, Assistant Professor, RMD Engineering College, Kavarapete. This subject for the 6th semester, third year students, 22 EC 601, Digital Signal Processing. It's a lab integrated subject. Yes, we'll start with the subject. I'll go with the first unit. Unit number 1 is discrete Fourier transform. Since it is a digital signal processing, so whatever discussion based on discrete signals. Okay, first topic is problems on DFT, discrete Fourier transform. Especially for the discrete signals, we'll use discrete Fourier transform or discrete time Fourier transform and also Z transform. Okay, first we'll go with the discrete Fourier transform. Discrete Fourier transform is nothing but Fourier transformation to be applied for any information or any signal in discrete, that called as samples. Further, we're going to discuss in terms of the problems. If we have some problem, show that with x of n as an n point sequence and x of k as n point DFT. I'll repeat again. Show that, so we need to prove x of n is an n point sequence. So you take any signal, maybe voice or speech, that is maybe x of n input signal. That will be the n point signal. N point sequence nothing but n is equal to 8, n equal to 4, 2 power n. That is they're talking about the n point sequence. Here n point sequence 2 power n. So n is an infinite value. It may be any value. And x of k as an n point DFT. X of k is my output signal, receiver part. That may be the n point DFT. That means my signal going to change. That means my input signal going to change as an output as x of k via transformation. My transformation is Fourier transform. Fourier transform means for discrete signals. Discrete signal means samples. Samples means n. So we are using x of n as the input, means it's a purely discrete. When I'm using discrete, so I need to change as a discrete Fourier transform. Okay, summation n equal to 0 to n minus 1 modulus x of n the whole square is equal to 1 by n summation k equal to 0 to n minus 1 modulus x of k the whole square. Little bit you should go through the signals and system subject. It's a prerequisite subject of the DSP. You have to remember the properties of the discrete time Fourier transform. Such properties are called as Parseval's theorem. I think you remember where you are using modulus over there. And also we will be using time scaling properties also modulus, but it's a scale factor. Once you take the modulus, there's no issues with the plus or minus value. Parseval's, especially Parseval, you will be very clear. So we need to prove. We need to go for the proof of this particular question. Take the LHS part. Summation n equal to 0 to n minus 1 modulus x of n the whole square, which is equal to. Can I write this modulus term as into the one term is a normal term, other one is a conjugate of the other term. That is nothing but summation n equal to 0 to n minus 1 x of n, x of conjugate of n. Next step, summation n equal to 0 to n minus 1 x of n. Take x of n is outside. Therefore, 1 by n summation k equal to 0 to n minus 1 x of k e power j 2 pi k n by n. This is the formula for x of n. So instead of x of n I am substituting for the x star of n. So I am replacing this x star of n, the whole value, into the star, which is equal to summation m equal to 0 to n minus 1 x of n 1 by n summation k equal to 0 to n minus 1 x star of k e power minus j 2 pi k n by n. Instead of you put n equal to 0 or m equal to 0, both are the variable term. Okay, so in side I can mention that n and m are both the same terms. Next step, n equal to 0 to n minus 1 x of n e power minus j 2 pi k n by n. It's nothing but a formula where we derive this is a derived formula of the DFT. Dot, separate this remaining term 1 by n summation k equal to 0 to n minus 1 x star of k. There are two different terms are there. Now the first term is nothing but x of k. This first term is nothing but your x of k term. So replacing here as a x of k. So remaining term 1 by n summation 0 to n minus 1 summation k equal to 0 to n minus 1 x conjugate of k, which is equal to 1 by n, that take the x of k to the inside term. So 1 by n summation k equal to 0 to n minus 1 x of k x star of k. 1 by n summation n equals 0 to n minus 1. We already started with the LHS part. Modulus means we will be splitted into the normal term along with the star term, that is called conjugated term. The same thing, that x star of k and x of k become modulus x of k. Therefore 1 by n summation k equals 0 to n minus 1, once both the term to be merged, it became a modulus whole square will come. So modulus of x of k the whole square, hence RHS. So I started with the LHS summation n equal to 0 to n minus 1 modulus x of n the whole square. I ended with the value of the RHS 1 by n summation n equal to 0 to n minus 1 modulus x of k the whole square. N showed with the x of n as a n point sequence for the n point DFT. Hope you understood. Okay, this kind of problem you can expect in the part C, or maybe some complex or a tough setting of question paper. You can expect this kind of question. Show that and prove that. Thank you, student. We will see more problem in the next videos.